Welcome back to my dear friends to the Tech Civil Learning. As you know, our channel is continuously insisting with providing the practical education to the students so that you can understand the concept very clearly. So my dear friends, I promised you just give me your 20 to 30 minutes time. You'll surely going to understand the concept which is mentioned in the thumbnails. So without wasting time, let's start the today topic. So let's see. My dear friends, we have already studied about the analysis of bars of varying sections in the previous lectures. So if you have not gone through that one, please go and watch the video so that you can understand the concept very clearly. So today we will especially deal about the deformations in the deformations taking place in the tapered rod. So we will analyze the uniform tapering circular rod, right? So without wasting time, let's see. Here we will going to derive a formula for the deformation formula for the circular tamping rod. So here we will find out, ultimately we will derive the formula of del L, right? DL, that is del L, that is deformations in the what you call tampering circular rod. So in this ones we will assume a bar of uniform tapering from diameter D1 and at the one end and the diameter D2 at the other end, right? So as you can see in these figures that I have assumed a what you call a uniform tapering rod of the diameter of this side is D1, at the same time the diameter of this side is D2, and this tapered rod is subjected to tensile axial load. As you can see, that is tensile axial load on the both side, right? Acting on the D1s as well as on the D2. Similarly, we will assume one what you call elemental strips, right? So that we can derive the deformations in the whole section, right? So we will assume that is one elemental strips of having thickness dx from the from x from the d1 diameter of the bar. So here the P is nothing but the axial tensile load acting on the bar on the both side at the same time. L is nothing but the total length of the that is bar, and the E is known as Young's modulus. As every material has on its certain value of Young's modulus, so we must have to consider the Young's modulus. So my dear friends, please try to concentrate on it so that you can understand it very easy, right? It's very easy. So here what I did, I have considered elemental strips of length dx, right? Its length is, this one is elemental strips of having length dx from the distance of x from the, that is what we call the, either you can say from the d1s or from the left hand, right? So here the as these sides if having d1s, similarly this is having d2, so we have assumed the diameter of this elemental strips is dx, right? Dx is nothing but the diameter of the elemental strips at a distance of x from the d1. So my dear friends, we will flow step by step procedures, right? Here just keep in mind that we have to find out del L, and del L can be only find we can only find the del L from the strains. So before that we have to find all this area, stress. So in steps 1 we will calculate the diameter of elemental strips, that is dx, right? Dx is nothing but the diameter of the elemental strips. So dx can be calculated d1 minus, that is d1 minus into d1 minus d2 by L into x, because it is acting at the distance of L. So we need to, sorry, it is acting at the distance of x. So we need to find the diameter of this one. So d1 minus d1 minus into d1 minus d2 by L into x, right? X is nothing but the, from the distance it is acting. So d1 minus d2 by L, right, means this side, here this side minus this side by whole L. L is the length of the bar into x, because it is acting at the distance of x. So you will get the diameter of the elemental strips. So here's what I have assumed. I have assumed that k is equal to d1 minus d2 by L. I have just assumed it. You can put it here p as you like, right? So here d1 minus, the instead of d1 minus d2 in d1 minus d2 by L, I have substitute, that is k. So d1 minus kx is the diameter of the elemental strips. So we have already calculated the diameters. So in steps 2 we will calculate the area of cross section of the that one elemental strips at a distance of x. Now we are calculating the area of the elemental strips, so it is denoted as ax. So area of the means any circular rod is pi by 4 d square. So here dx square, because x is the elemental area, so pi by 4, and the dx value is d minus kx from the above means steps 1 square. So we have already calculated the diameter, and from the diameter we have calculated area. So now we'll calculate the stress produced in that bar due to the external load, right? So in that one, stress of the strips means there will be induced of stress due to the action of the external load, that is axially tensile loads. So elemental of a strips means denoted as sigma x, that is means what is called stress of the strips, that is load by area, as you know. So load is P, that is means axially tensile load. At the same time, area we have calculated above, that is pi by 4 d1 minus kx squares. So here the if you means resolve it, then P will go up, right? Because P will go up if you resolve this one. So means 4P by pi d1 minus kx squares. So almost we have calculated half of the steps. So we have calculated a stress. Now we will calculate a strain of the element of dx, right? Means what will be the strain, means or what will be the deformations due to the means what you call stress in the elemental strips. So a strain is means denoted as means a small ex, and we know that a strain is nothing but the stress by Young's modulus. So a stress is denoted as sigma x, and Young's means Young's modulus is capital E. So here we have already calculated sigma x, 4p by pi into d1 minus kx square. I have written this ones is means into 1 by e. So we can write this ones, or else you can means substitute e value means here only, no problem. You can do it in your own way. So 4p, that is pi e d1 minus kx square. So we have calculated the means deformations in the a strain in the what means rectangle, means what you call the tempered circular rod. So now we will calculate how much change in length, or how much means what you call elongations takes place due to the means what you call external load in the strips. So means as you know my dear friends, आपको पता है कि stress means strain is equal to nothing but the change in length, that is dl, change in length by original length. So this is the formula of means what we call strains. So we have to calculate the extension, right? Means extension or the change in length, that is dl. So dl is equal to means here dl is equal to nothing but the strain, that is E, strain into original length. So here same I have did here. So d means dl is equal to ex. Ex is nothing but the what we call strain in the elemental strips, and here the means dx is the original length of the strips. Okay, we are not considering here the means whole section strips. Now we are calculating all these means what we call strains of the elemental strips only. So dx is the length of the elemental strips. So we will substitute ex value, that is 4p by means pi e d1 minus kx into dx. So this is the equation gives the extension of the small elemental strips of dx. So this equation is used to calculate the deformations or the extensions taking place in the elemental strips. So my dear friends, now we need for the whole whole circular rod, whole circular tempered rod. So for calculating means whole circular, we must have to integrate, right? Because this is the means a small means this is equation for the small elemental strips. If you need the full deformations taking place in the means what you call circular rod, then we must have to integrate with 0 to limit 0 to L, right? So now you can say now you must have arise a question that why the limit is 0 to L. Wait my dear friends, I will show you. Here suppose imagine the length of the bar is here 0, then we have to calculate means the deformation for the whole sections, then of course the length here will be L. So that's why we are taking limit at 0 to L, right? Means 0 to L is the means covering all the means what you call covering overall means length of the bar. So here the 0 is means indicated as the means origins, and L is indicated as the final length. So that's why we have taken the limit as 0 to L. So for means total extensions of the means what we call circular taper rod, I have means integrated 0 to L of the equations means of the extensions of the equation for the elemental strips, that is 4p pi e into d1 minus kx square into dx. So here we know that 4p by pi e is the means what we call constant term, so we can take it out, right? These terms can be take it out, right? So I have these terms take means I have taken these ones out. So 0 to L d1 minus kx square and minus 2, right? Means initially it was can be written as 1 by d1 minus k x, right? Means square. So if I put these terms upward, so these ones means what you call 2 becomes negative, so d1 minus k into x minus 2, and I have removed this one, so it means dx. So now we'll multiply means or divide by minus means what you call minus with the minus k, so that it becomes simple to means to do the means integrations. So what I just multiply or divide by means minus k, so I multiplied here and divide by k here. So means while we do integrations now, then it must comes d1 minus kx minus 1 and into minus k. So this is the integrations of these terms and the limit 0 to L. So I can write these terms as, because this one minus into minus it become plus, so the k is positive. So d1 minus kx means bracket minus 1s can be written as 1 by d1 minus kx, because I have to remove these ones minus k. So 1 by d minus kx, right? It can be written as, and this one's k comes out, right? It is as constant, it comes out. So now we'll substitute the value of L in the place of x, right? X in the place of x we'll substitute means L. So means 4p by that pi e k into that 1 by d1 minus that is k and into L, right? Instead of x we'll substitute L. So minus means again we'll substitute in the value of x we'll substitute 0. So 1 by, if you substitute 0, the whole term becomes 0. So 1 by d means d1s. So from here, my dear friends, means what we know, we have substituted that k is equal to d1 minus d2 by L in the above first equation itself, right? So what we'll do now, we'll substitute the value of k in the place of, right, k. So we'll substitute d1 minus d2 by L in the instead of in the place of k. So now we'll see what will be the equation. So just substitute. So 4p by pi e in the place of L, we will substitute d1 minus d2 by k. Similarly, d1 minus d2 by k means what you call d1 minus d2 by L. Here it will be L, my dear friends, L, and minus 1 minus d1. So 4pl, L goes up. So 4pl by pi e d1 minus d2. Similarly, if we multiply means this d1 minus d2 by L, right? So this what happened here, this L and this L will be cancelled. So d1 and minus d1 and the minus plus d2 minus d1 by means minus 1 by d1. So similarly 4pl pi e d1 minus d2, if we means if this one d1 and d1 minus plus get cancels, so 1 by d2 minus 1 by d1s, if we means solve these ones, then it must comes d1 minus d2 by d1 into d2. So this one got cancels. So finally we got 4pl pi e d1 into d2. So this is the means formula for calculating the elongations or the deformations in the circular tampering rod. So as it is uniform, you can also write it as, right, means d is equal to d1 minus d2. So it means if you put only d instead of d1 minus d2, then 4pl pi e d square. So this is the elongations formula for the circular tampering rod. अगर कोई आपको पूछेगा, if anybody asks you what is the formula for calculating the means what you call deformations in the circular tampering rod, then it is 4pl by pi e d1 minus d2 square. So now we will analyze for the rectangular bar. Above equations what we have analyzed is circular bar. So my dear friends, here the procedure is same. We must have to calculate the means area, then the stress, then the strain. Similarly we will calculate all these things for the elemental strips, then later we will integrate it and calculate for the what calculating for the means whole area section. Similarly here I have also assumed that is the rectangular means sections of having one inside is A and the other smaller side is B. Similarly elemental of area of having length dx from the means dx at a distance of x from A. Similarly and I have assumed that the thickness of these elemental strips is right, the thickness of the rectangular bar is, that is this thickness of the rectangular bar is what I have assumed is T. So the thickness of it is T. So here P is means same procedure, P means what you call axially tensile load, right? L is total length, here A is width at the bigger end, B is width at the smaller end, Young's modulus value, and the T is the thickness. Similarly now we will calculate. Now in the circular we need to calculate the diameter for calculating of the area, but for the rectangular we need to calculate the length, means what you call breadth, width and depth. So here in the steps first we will calculate the width of the bar at the sections x-axis. Similar means the width of the bar of elemental strips. So here A minus these ones, if you need to calculate its width, this width, then A minus into A minus B minus means divided by L into x at a distance of x. So similarly that once A minus B by L will substitute the means value of means we will assume it is as K. So A minus Kx is the width of the elemental strips and the thickness of the elemental strips is T. So from here we can easily calculate the area of the elemental strips, that is width into thickness. So A minus Kx into T. Finally A minus Kx into T is the means what you call elemental area of the sections. Similarly now we have area, then we can easily calculate a stress of the elemental strips. So load by area P by A minus Kx into T. Now we got the stress. Now we will calculate the extensions that is del L. Del L is nothing but the strain into means length of the means what you call length of the elemental strips. So length of dx. So means strain is nothing but the stress by Young's modulus into dx. So we have means a stress value, that is P by means A minus Kx into T, and the Young's modulus value is E into dx. So if we means solve these ones, that P means it substitute here, right? Here it will substitute, then E into A minus Kx into T by dx. So this is the extension formula for the elemental strips, and for the total extension we must have to means what you call integrate of limit of 0 to L. So P by AE means P by E into A minus means Kx and into T, this one is nothing my dear friends but T into dx. So P by means P by ET, that's what ET is constant, so we will take it out, right? P by ET will take it out. So limit means 0 to L, that is 1 by A minus Kx. So 1 by x of the integration is nothing but the log E, right? So log E means 1 minus Kx. So means limit 0 to L, and this one is constant, so into 1 minus K. So means this one is minus, we will take this minus to the initial position. So minus E by means ETK log E, and this one's 1 by K is written as log EA, right? So means P by ETK, right? If we multiply this minus with these terms, then this become positive. So log EA minus this become negative. So minus log E, it means into A minus K. So from these ones we can write it as log E is equal to A by means A by A minus KL, because the properties of the means what you call algorithm. So we can write as log E is equal to A by A minus KL. So here now we will substitute the value of means K, that is K is nothing. Here we know in the from steps 1 A is equal to A minus B by what? T. Sorry, A minus B by L. So A minus B by L, right? Similarly A minus B by L will substitute. Then if we will resolve this ones, then we will get that is P into L by ET A minus B into log E A by B. So this is the formula of the extensions for the rectangular bar. Remember, for the rectangular bar. So my dear friends, means if you know these ones, you can solve the any numericals right? So I have taken the two easy numericals so that you can understand the concept and you can go through it. If you have any doubt, if you need anything, then put your comment in the comment box so that I can understand. So here, my dear friends, we need to calculate the modulus of elasticity, that is E. For what? For the rod, for rod which tampers uniformly of 30 to 50 mm diameter. Here the diameter is given, then we must understand it is what you call circular tampered rod, right? Is of having length 350, then the rod is subjected to an axial load 4.5 kilonewton and extension of the rod is given. So everything is given, just we need to calculate the value of Young's modulus E. It is very easy. Here the diameter is given, large side diameters. If this one, right, the figure will be, figure is like this ones, right? Here this one, this side diameter is given, this side diameter is given, total L is given, right? And here this one subjected to 5.5 kilonewtons. Here the extension is given due to this one load. So where the Young's modulus value is what? So my dear friends, we know this formula, total extension is equal to 4PL by pi E d1 into d2. So here we just need to calculate E. Agar if it is in the given that we have to calculate P either L, then you can calculate, just you can calculate anything from these equations. If it is E is given, then you have to calculate P, then you can also easily calculate. If it is all the what you call required dimension is given, if you need to calculate L, then you can also calculate. If it is need to calculate D, then you can also calculate. So it's very easy. Just for the understanding purpose, I have taken one easy problems. So here the extensions value is 0.05, 4 into P value is given, L value is given, pi value, E value, and D1, D2. So just I have take it out and I have substitute here. So 4P by, and finally the Young's modulus value comes to 17865 Newton per mm square. So this is the value of Young's modulus of the tampered rod. So we'll see the next numericals based on the rectangular tamper bars. So here, my dear friends, as you can see, the extension the rectangular steel bars. If it is rectangular steel bar, then you must have to remember the formula, which is right now we have derived. So the length of the bar is what you call 400 and its thickness is 10 mm, right? And is found to be extension is found to be 0.2 what you call 0.21 mm, and the bar tamper uniformly width, this one is width is given, Young's modulus value is given. Just we have to calculate what? We have to calculate P is equal to what, how much load is acting on the bar. So here everything is given. We know the formula of the rectangular extensions, that is PL by ET A minus B into log E A by B. So we'll substitute here and we need to calculate P. So G this value is given, so P into 400, and we'll substitute all this value. Then we'll resolve these ones, right? 400 by 2 into 10 to the power 5 into 10 into 100 minus 5 a log 100 by 5. So we'll if we calculate these ones, then the value comes 0.00004 P into 0.69, that is there is a log value these ones. So we need to calculate this P value, then substitute all these things in that side and divide it, then you will get 75746 newtons. So this is the concept related to. So thank you for watching our video. If you like it, please don't forget to share it and subscribe my channel so that you will get the notifications once I upload the video. So thank you for watching and bye bye, take care yourself. Thank you.